In the last video, we took a look at the first law of thermodynamics, and we made some allusions to the second law of thermodynamics. Here we're going to present the second law of thermodynamics and also get in a little bit into its statistical formulation. We'll cap off with a very quick presentation on the third law of thermodynamics. So, at issue in physics is that there are certain processes that we call irreversible. And what we mean by that is, for instance, imagine that you have yourself a teacup that is precariously perched on a countertop. And then eventually it falls off, flies down onto the floor, and smashes into a zillion bits that go flying all over the place. As we've seen, those teacup shards are going to eventually collide with air molecules in the room, increasing the average kinetic energy of the air molecules, so the thermal energy is going up. So eventually we end up with the temperature of the room increasing. So that's one possibility. Now, seemingly strangely, the laws of physics also permit for the reverse process. So here, what we would imagine happening is that we have a whole bunch of teacup shards on the floor. The temperature of the room drops slightly, and air molecules collide with the teacup shards. They collide in just the right way to spontaneously reassemble a teacup. It goes one half flips up to the surface, up to the counter, and ends up perched precariously on the counter as a completely and perfectly reassembled teacup where you can't see any cracks at all. So, like I said, that is perfectly permissible by the laws of physics. You can write down the equations for it. So either one of these laws of physics are totally good with. You can totally see that one. You can totally see that one, according to the laws of physics. Now, the next question, since physics is an experimental science, is, do we actually see it? And we've probably all seen a teacup break into a zillion pieces falling off a ledge, or at the very least you know somebody who has seen that happen. And I sincerely doubt that you or anyone you have ever encountered has ever seen a pile of teacup shards spontaneously reassemble and fly back up to the top. In fact, if someone were to, in serious earnestness, suggest that they had seen such a thing, you would probably go and urge them to seek medical attention. So, all right, so this is a conundrum, because if the laws of physics say it's possible, how can we never see it? That's why we call it irreversible. We can have the process happen in the forward direction. We smash the teacup. But the reverse process of spontaneously reassembling a teacup never seems to happen. So where can we go from there? Well, it turns out that we can introduce a quantity called the entropy. Now, there are a couple of definitions of them, and I'll be skipping one of those definitions in this treatment. But suffice it to say, a little later in the video, we will show that there is a quantity called the entropy. Its units will be joules per Kelvin. That, very roughly speaking, is the phrase usually used in books is I measure the disorder of a system. I don't quite like that. I like saying that it's a measure of the number of accessible states of a system. In other words, the number of different possibilities you can have. Like, for instance, there's only so many ways you can have a neatly organized sock drawer where all of your socks are paired together by design, and the designs are all in all they're all laid out nice and neatly in the sock drawer. You can basically swap the sock pairs around, and that's about it. There are many, many ways to have what we would call a disorganized sock drawer, where you just plain chuck all the socks in. Maybe some of them are inside out, maybe some of them are right side out. Certainly, they aren't paired together. The socks are all sort of higgledy-piggledy, and if you're to go in and stir the drawer, it would, for all practical purposes, look just as organized as before. So that's what I mean. There are many more possibilities to be disorganized than to be organized. And so people tend to push that a little too far and say entropy is a measure of disorder. But it's really more accurate to just say it's a measure of the number of possibilities that a system can currently be in. So it turns out that we can state the second law of thermodynamics that for a closed system, the change in the entropy of a closed system must be positive semi-definite. And you can only have this equality here if a process is reversible. In other words, that you can just as likely have a process go forward or backward. So, in practice, though, truly reversible processes you can show have to literally take forever to run. And so, as a result, in the real world, we're never going to have the equal sign. But it is there. Okay. So what does this get us? Well, this gives us an arrow of time. Since we can say that time progresses in the direction that teacups want to break, right? We can say that time flows in the direction of increasing entropy. So, and this helps to resolve the puzzle, since the laws of physics would be perfectly happy if you ran time backwards and had teacup shards reassemble spontaneously. Here we can say, no, it flows in the direction of increasing entropy. And a way to think about that, if it's helpful, and if it's not, don't get too stressed out about it, is that we remember the past, but we don't remember the future. And the act of building memories is going to involve you having to organize your brain. Now you'd think, wait a minute, that, men make neural connections. And you'd think, wait a minute, if I'm having to make my brain more organized, isn't that decreasing the entropy of my brain? And the answer is yes, but in doing so, you'll have to expend an awful lot of ATPs to make that happen. All sorts of cell respiration is going to happen. And you're going to be breathing in and out. And it turns out that you will, as process of your metabolism, you'll end up transferring a bunch of heat to the air surrounding you. By increasing that heat, that allows the average air molecule to be able to move at a greater range of velocities. So there are more possibilities for the air molecules to explore. So although your brain got a little more organized, you've vastly increased the number of possibilities, or if you will, the disorder of the air around you, way more than you organized your brain. So that way you can say, okay, that's why I remember the past, but I don't remember the future. This isn't the only era of time that physicists have identified. It turns out that there are a few others. The next most accessible of these eras of time is to say that time flows in the direction of the asymmetry of decays of a certain subatomic particle called a neutral kaon. And then it gets weird from there. But all of these arrows of time that we've been able to identify, they all point in the same direction. So although we don't know what time is, we do have these different physical phenomena that reliably point in the direction of increasing time. Now, as we've been going along in thermodynamics here, you've seen that I've generally presented more than one statement of each law of thermodynamics. So here's another one. And it goes, heat cannot... Actually, here there are two. Let me give you... you can show that no heat engine can exceed the Carnot efficiency. Again, here I'll skip over the details of arguing that this engine is the most efficient possible heat engine and just focus on the fact that it is a cycle that runs perfectly reversibly. So it's a limit of what we could ever possibly achieve, because in order for something to run perfectly reversibly, it would take literally forever to run a cycle. In fact, this is something you can see as any kind of engine gets more and more efficient. You actually do start to see a point where the RPMs of the engines necessarily must decrease, because as you're getting closer to running more and more reversibly, you have to run slower and slower. So in the limit of this ideal engine that would run forever, you can show that this requirement that the entropy of the universe always increase requires that no heat engine can exceed the Carnot efficiency. So that's another statement of the second law. Still yet another statement of the second law is that heat cannot be spontaneously transferred from a cold object to a hot one. Now, this doesn't forbid heat pumps, which we've already seen. There you're doing work to move the heat. That's okay. What's not okay is just to take a cold object, butt it up against a hot object, and have the cold object get colder and the hot object get hotter. There are two ways that you can argue this. So let's go and draw an energy transfer diagram for this. Excuse me. T hot, T cold. So here we're trying to move heat from cold to hot. And the second law of thermodynamics says that to do this without introducing any work is impossible. In a more detailed analysis, what you can show is that when you remove heat from the cold reservoir, you decrease the number of possible states that atoms can have in the cold reservoir. So its entropy will go down. And by the same token, as you introduce heat, like I was discussing before, the entropy of the hot reservoir will go up. And you can show that in this case, the entropy of the cold reservoir will go down by the entropy of the hot reservoir will go up by less than the entropy of the cold reservoir goes down, and so this would require the change in entropy of the entire system to be negative, violating the second law of thermodynamics. Another way we can argue this is to think about how we would actually build such a thing out of heat engines and show that that's going to be problematic. So, so let's start by so we'll have a common reservoir here, two common reservoirs, and we are going to have we're going to start by hooking up a refrigerator that will be transferring heat from the cold reservoir. So we'll call this Q cold refrigerator, Q hot refrigerator. And so in order to do this, you're going to have to hook up, you're going to have to input work in to make this happen. You're going to have a legitimate heat pump. So how are we going to do that? Well, the only way we can imagine doing that is if we go ahead and hook up a heat engine to that. So we'll say Q hot engine, Q cold engine. Okay. So now the issue here is that let's say I go ahead and I make this engine a Carnot engine. All right. So that's the most efficient possible engine I could have. What would happen? Well, I could imagine hooking up a Carnot refrigerator here. And then here's the thing, is that the Carnot refrigerator would only be able to move the heat back out that got rejected in by the Carnot engine. It wouldn't be able to move any more than that. In order to net out with an upward flow, you would need a better than Carnot engine. So, because better than Carnot refrigerator. And so since you can't have either a Carnot engine or you can't even have a Carnot engine or a Carnot refrigerator in real life, and not even theoretically can you have one that's better than that, that means that it's impossible. You can't have a system that moves heat from cold to hot without work coming in from outside the system. So heat cannot be spontaneously transferred from a cold object to a hot one, and that should say from there. We're going to continue that to get a better idea of what entropy is, and to connect that to a statistical interpretation of things. But we'll start with another restatement of the second law. So here I'll define a perpetual motion machine of the second kind. It'll turn out that a perpetual motion machine of the second kind does not violate the first law, but it does violate the second. Perpetual motion machine of the first kind turns out violates both the first and second laws. A perpetual motion machine of the second kind is a perpetual motion machine that does no useful work. So all it does is just literally run forever. It doesn't do anything. And the restatement of the second law is that it is impossible to build one of these things. So here's a way to think about that. So let's say we built such a device. What would it look like? Well, you'd still, with any engine, you still have to have a hot reservoir, a cold reservoir, and a working substance. So we would be flowing heat out from the hot reservoir. And we would say, okay, since all we want to do is run this forever, we'll just take the work and we can, the work output, and hook it up to a paddle wheel or something, do Joule's experiment to do work on the substance in the hot reservoir. However, it's still the case that you have to reject heat to the cold reservoir because the Carnot efficiency of a heat engine can never be equal to 1. So there's no way that you can get the work to equal Q hot. So it's going to be less than Q hot. And so that means that every cycle you will be rejecting heat to the cold reservoir. This means ultimately you'll be dropping the temperature of the hot reservoir, raising the temperature of the cold reservoir, and eventually you'll just come to a halt because there isn't any more heat to flow. So that's a schematic view of that. Now with that, going into doing a statistical formulation, the general treatment of that, it gets very hairy and is beyond the scope of this class. But we can take a look at what physicists like to call toy models. Systems that in principle you could build very simple ones that hopefully clarify the point. So let's just imagine that we have a box. We're going to paint a line down the middle of the box, and we put 4 molecules into the box. That's it. So there's molecule number 1, molecule number 2, molecule number 3, molecule number 4. So it'll always be the case that a molecule is either on one side of the line in the box or the other. So we can say the number on the left side plus the number on the right side in this example would always have to be equal to 4. But how many different ways could we actually arrange all those atoms if we want? Well, let's start making a little table. We have atoms 1, 2, 3, and 4. And let's see, one way we could do it is we could have all the atoms on the left side. So the essential issue here is that they're all on one side, none of them are on the other. So we'll also keep track of what we call the configuration. So this is just the number on the left side, number on the right side. So there's 4 here, 0 here. And there's only one way that we can possibly get this arrangement. So we call this the multiplicity of microstates. This will hopefully make more sense in a second. And the symbol for this is either W or a capital Greek omega. But anyway, this is just counting the number of ways that we can have 4 on the left, 1 on the right, and here there's only one way. All right, how about having 3 on the left and 1 on the right? Well, turns out there's 4 ways you can do that. You could have, say, atoms 1, 2, and 3 on the left, atom 4 on the right, or 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Oops, sorry. 1, 2, 3, 4. So it turns out that there are 4 ways you can arrange this. You can either have atom 1, 2, 3, or 4 on the right hand side. Now the thing is you can't tell the atoms apart So the only thing we can conclude is when you look in the box and see which side of the line the atoms are on, it is 4 times more likely that you'll have 3 atoms on the left, 1 on the right, versus having all 4 on the left. Okay, well, let's go take a look now at what if we had 2 and 2. How many ways can we do that? Well, we can have numbers 1, 2 on the left and 3 and 4 on the right. And then we'll just leave number 4 on the right here while we move number 3 along. So L, R, L, R, R, L, L, R. So we've got 3 there so far. And then let's see, next one we could do that's different is we can start moving the right one over. So we'll start here, put this guy over there. That would be a new configuration. R, L, R, R, L. Move this atom over. R, L, R, L. And then finally R, R, L, L. And that's it. So all the possible ways you can put 2 on the left, 2 on the right. Turns out that there are 6 ways to do that. And again, we call this a microstate because, again, there's no way that you can draw tiny little 1, 2s, 3s, and 4s on the atoms to know which atom is which. So all we can say is that's 6 times more likely to have 2 left, 2 right than it is to have all 4 on the left. And by the same token, it's 1.5 times more likely to have 2 left, 2 right than it is to have 3 left, 1 right. All right, so we can go ahead and finish out the table here. And this is just going to be symmetric. The next configuration we can look at would be if we had 1 on the left and 3 on the right. And that's just like the 3 on the left, 1 on the right deal here. So we could have number 1 be on the left and these 3 be on the right. There we go. And again, there are 4 microstates of that. So we would conclude that that's just as likely as having 3 on the left, 1 on the right. And finally, just to complete it all out, there's only one possibility left. And that possibility is if all 4 of them are on the right. And there's exactly one way we can do that. Okay. Well, that was a lot. But the idea here is that since the atoms are running around randomly, whenever you look, any of these microstates are equally probable. And that is the big underlying assumption in statistical mechanics. Oops. Let's do a better job with that. There we go. And from this assumption, Boltzmann came up with an expression for entropy. By the way, if you want to calculate the general case for the number of microstates in our left-right system here, if capital N is the number of atoms, and then the number of microstates where you have NL on the left and NR on the right is this, or it's the number of atoms factorial divided by the number of atoms to the left, factorial, and the number of atoms to the right, factorial. And if factorial is ringing a very, very vague bell, you often see it when you do the binomial theorem in algebra class. Just a quick reminder, of that is that 0 factorial is equal to 1. You use an exclamation point for factorial, and you always put it after the number. 1 factorial is also 1. And then 2 factorial is equal to 2 times 1, which would be 2. 3 factorial is 3 times 2 times 1, which would be 6. 4 factorial would be 4 times 3 times 2 times 1, which would be 24, etc. Anyway, this is the how we could count the number of microstates for our left-right system. And to do it in a more general way, where we're not just saying, well, it's either on the left or on the right, which sounds awfully artificial, but there is actually a legitimate system called an icing gas, where something similar to this is happening. And so it is sometimes, there is for one specific case, this is a valid model for describing things, but in general, you've got to be do a little more work, and there are these things called partition functions and stuff like that that we don't really need to get into. The upshot of it all is that Boltzmann figured out that for any particular for any particular configuration, you could calculate the entropy. And what he got was that the entropy was equal to the Boltzmann constant times the natural log of the number of microstates. So what does this mean? Well, if we go back and look here for these systems where, say, everything was on the left or everything was on the right, those were low probability systems. And here the multiplicity of microstates is 1. If I take the natural log of 1, that would be 0. So that would be the lowest my entropy could be. On the other hand, the entropy of having 3 left, 3 right would be k times the natural log of 4. And 2 and 2, the entropy of that state would be k times the natural log of 6. And so if you have a system prepared in a low probability state, like for instance, all 4 of the atoms are on the left side of the box, if you were to close up the walls of the box and then open up the box later and take a look, the odds that when you look, all 4 are on the left at that time are rather low. The odds that you're going to have some mix of atoms on the left and the right side is pretty high. And so when you take a look, you're probably going to have be in a configuration that has a higher number of microstates, which has a higher entropy. And so then we say that the entropy will increase. Now, when you're dealing with small numbers of atoms like this, these low probability states, what people often will view as ordered, although being ordered is something that is in the eye of the beholder. This is what gives people the idea of saying that nature evolves towards disorder, is that if you view something like, say, having all 4 atoms on the right side as being an ordered thing, then if you choose to view these states as being more disordered, then yeah, you're evolving toward disorder. But it's really just more accurate to say that you're evolving from low probability states to high probability states. Now, with a small number of atoms, getting back to these low probability states that say all 4 on the left or all 4 on the right, is still kind of good. So I queued up a computer simulation here say, well, what happens if you flip 10 coins? You can see, yeah, okay, it's still a pretty good shot of being in any state here. Definitely more likely to have 5 atoms on the left and 5 on the right. But, 0 and 10 are, this is kind of the number on the right. Having 0 on the right or 10 on the right, it's still not totally gone. But certainly there's a good chance of occupying just about anything. Well, we can go ahead and say, well, about 11 atoms, 12, 13, so forth. And in fact, I started doing saying, well, what about, 100 atoms? By the time you get to 100 atoms, the odds of having ever anything more than, say, looks like about maybe 36 to the left or 64 to the right is so small that in practical terms it's probably never going to happen. So if you have a state that was prepared where all the atoms are on the left or right side of the box, what you're going to find is that after you let the system evolve, anytime you look, the odds are overwhelming that you're going to find the number of atoms be somewhere in the neighborhood of 50-50 split, with the extremes out to maybe 60-40, 40-60. But everything's going to be mostly clumped right around the 50-50 split. That's with 100 atoms. Let's let this go. All right, so now we're up to 500 atoms in the box. And you can see the odds are overwhelming that you're going to be on a 50-50 split or within a smaller neighborhood around 50-50 percentage-wise. Looks like here maybe you go from about 220 out to about 280. So even though in absolute numbers of atoms, the number of with the distribution is getting bigger, as a percentage of the number of atoms in the box, it's getting closer and closer to always hanging right in the neighborhood of a 50-50 split. Let's let this run up to 1,000 atoms. Whoop. My bad. Doggone it. All right, here we go. So let's take it up to 1,000 atoms. By the time you get to 1,000 atoms, you can see it's ever heading as we have more and more. The odds that you'll be at right around a 50-50 split, in the neighborhood of a 50-50 split, get ever better and better. And the deviation off of 50-50 as a percentage of the number of atoms gets ever less and less and less. So that's just if we have 1,000 atoms in the box. Now, in a real world situation, you're going to be talking about having something on the order of a mole of atoms, so 10 to the 23rd. So by this point, the curve basically will end up looking pretty much like a straight line poking straight up, and anything that isn't in the absolute immediate vicinity of a 50-50 split has probability so small that you'll basically never, ever, ever encounter it. One of the classic problems that physicists learn to say, what do you mean by practically speaking you'll never see it, is we get asked to calculate as a homework problem the odds that if you had one monkey banging random letters on a typewriter, what are the odds that that monkey will bang out a perfect page from Shakespeare's play Hamlet? Odds are really absurdly small. So then you say, okay, let's help that out. Let's make it 100 monkeys banging on 100 typewriters. Doesn't help much. So then you say, okay, what if every single atom in the universe were a monkey banging on a typewriter, and the monkeys are banging on the keys with 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 one keystroke per orbit of a hydrogen atom. It turns out that even in that situation, it would still take, if I remember correctly from when I did it, or on the order of about 1,000,000 times the lifetime of the universe, if every single atom in the universe were banging out random letters to try to make a page of Hamlet. And then what you get is when you look at things like, a mole of gas, to have, say, all the atoms be on the left or all the atoms be on the right is a probability so much more absurdly lower than a monkey accidentally banging out a page of Hamlet, that although on paper it's possible that all the atoms in a room could potentially rearrange back over to one side, none of us will ever live so long as to see that happen. So that's where we're going with that. So although on paper it's still possible, even here at the 1,000 atoms, it's possible that you could have 800 atoms on the right side of the room and 200 on the left, but the odds are so vanishingly small that you'll never live long enough to see that happen, even if you kept checking in on the state of the box at absurdly frequent intervals. Now, I can't leave a discussion of the laws of thermodynamics without presenting the third law of thermodynamics, so that's what I'm going to go ahead and do now. So in the third law of thermodynamics, again, it wouldn't be me if I weren't giving you at least two statements, so I will. One statement of it goes, as temperature approaches absolute zero, the entropy of a system approaches a constant. Or, this is an equivalent statement, it is impossible to reduce any system to absolute zero in a finite series of operations. So what corollary of this is that you can get a system to get as close as you like to absolute zero. For a long time, the record was 0.9 nanokelvin, but you can't actually get there. The gist of that is basically, in order to get some system all the way to absolute zero, you would have to somehow reject all the heat outside the universe. But since the universe is all there is, there's no place that you could go and reject the heat to. So you're on your own for remembering the 0th law of thermodynamics, but I can give you a cute mnemonic for remembering the first, second, and third laws. The first law of thermodynamics can be remembered as you can't win. This means you can't build a perpetual motion machine of the first kind. Sorry, no free energy for you. Second law, you can't break even. And that means you can't build a perpetual motion machine of the second kind, because a machine that would just plain run forever without doing anything would be breaking even. But it turns out that no, they all have to come to a halt. And then to remember the third law, is you can't quit playing. So the reason here is that if you were to get a system down to absolute zero, it turns out that that system would have to quit interacting with the rest of the universe altogether. So it turns out that at least at some super, super weak level, things have to you have to keep interacting with the rest of the universe. So you can't win, you can't break even, and you can't quit playing.